And I'm going to paste on the next. Okay, I'm going to take this whole thing across. Okay. If we were to cover the bottom, okay, if we were to cover the bottom, oh, I think I need to bring forward all the way. Okay. If I were to cover the bottom, okay, and expose the top only, right? What does this structure look like? Okay. Before I make you get an answer for you, I want you to look at this also. Okay. I want you to view this also. And I'm going to shrink it. Okay. So you can observe, right? If I were to cover the bottom, right? The top, what does it look like? Anyone? Is it a box beam or white flange? Anyone? I hope you're there. Box beam, you are absolutely right. Now, if I were to cover the top, right? Cover the top, right? Now it looks like what? White flange, yes or no? Right? So that's the confusing aspect of this question. Okay. So we realize that this structure is a combination of what? So we realize that the structure is a combination. It's a combination of box beam and white flange. Okay. So we are going to find the shearing stress at point B first. Okay. So we are going to find the first thing we're going to find is we're going to determine the shearing stress at point B. Okay, at point B. So I'm going to again take the whole thing. Maybe I just take the image. Okay, we're just going to find point B. Now, based on observation, okay, by looking just based on observation, we can more or less draw where the centroid is. Okay, so the centroid is dead on the center. Why is it dead on the center? If you look at the flange at the top is 2 inch by 0.2 inch, right? So if you look at the top flange, which I'm going to highlight now, right? And if you look at this geometry over here, this is also 2 inch by 0.2. Okay, so the first moment of area at the top and the bottom where I put my centroid line is exactly at that position. So we are aware that the distance from here to here is 1.5 inch. Okay. So we know that this is our centroid. Okay. So now we would like to determine the shearing stress at point A. But before I go on, we know that the formula we're going to use is shearing stress is equal to V Q over I T. Okay. Now, what we were given is that tau max is equal to 10 times 10 to the power 3 psi. Okay. So if we were to look at tau max or this formula over here, right? We know that the terms that are highlighting in yellow now, right? These two terms are constant. Okay, they are constant. Now where the location of tau max, okay, so tau max will occur either at Q max or T min, minimum thickness. Okay, and because we are doing thin wall analysis, at point B, the thickness is in this direction, right? At point A, the thickness is also measured in this direction. I'm going to call a point C. Okay, we're going to call this point over here our point C. At point C, the thickness is what? 0.3 inches, sorry, not millimeters. But at point C, right, we know that Q is going to be at its what? Q max, right? And we know that at point A, right, T is equal to T min. And likewise at point B, right, T is equal to T min. Okay. So the statement that we make that tau max will occur either at Q max or T min, we need to check. It's like your term test question, yes or no? I ask you to find the maximum shear at the centroid, and I ask you to find the maximum or the shearing stress at the centroid, and what is the maximum shearing stress, because the thickness is not constant. Okay. Now for this case, we have a thickness of T min of 0.2 and 0.3, right? At point B and point A, thickness is equal to 0.2. At point C, no doubt thickness is at 0.3. However, Q will be at its maximum. Okay. So now we are going to find our shearing stress at point A, point B, and point C. Okay. So now we are going to find final. We're going to find I have a question. White flash. Oh, it's not a question, it's just a comment. Sorry. We're going to find the shear stress at point B. Okay. So if we were to look at the shear stress at point B, the area we have to consider is this entire area. Okay. We are going to consider this entire area over here. And if we look at how our shear flow is designed, this is our terminal. You have one Q moving one side, one Q moving the other side. So you have one Q going towards the left, one Q going to the right. Okay. So for this case, I usually like to write that we have 2Q, right? Based on the area we specify, right? One Q go towards the left, one Q go to the right, and we know that the thickness is equal to 0.2 inch. Okay. So now we want to find the first moment of area of point B, which is equal to width. I like to go with depth multiplied by y bar. Okay, so I'm going to draw a transformation over here. So this is y and this is z. Okay, and before we go there, this is equal to 2q, or sorry, before we say that it's equal to 2q, right? And if I were to bring this box down, right, we realize it is a box beam. When it's box beam, you just declare that this is 2q. 1q go towards the left, 1q go towards the right, right? So from here, it is weird. It's okay. So from here, we are going to write down the width. So the width is equal to 2 inch minus 0.3 on either side. So 2 minus 0.3 minus 0.3, right? And then the depth is equal to 0.2. And then the y bar is 1.5 minus by 0.2 divided by 2. So this will become 2 minus 0.3 minus 0.3 times by 0.2 times by 1.4 is equal to 0.392 inches cubed. Okay, and then from here we can determine our shear stress at point B is equal to V and I are constant. Okay, V and I are constant. We're going to do everything in terms of V and I. For this reason, later on, you realize that we actually no need to find the second moment of area for this problem. Okay, so the Q is equal to Q. I'll write out the formula first. So this is equal to V over I. Q is equal to 0.392 divided by 2 divided by thickness of 0.2. The 2 over here is because this is, we have what? 2Q. Okay. So 0.392 divided by 2 is equal to 0.98 V over I. Okay. So that is the shear stress at point B. Next, we want to find the shear stress at point A. Okay. So again, I will copy this diagram. Right. Sketch out the position of the centroid. Cover the part that we don't need. Right. And then design the shear flow. Okay, now the left and right are independent, right? They are not, there's no, so this is our terminal. Right, this is also our terminal. The terminal on the left is not related to the terminal at the right at all, okay? And why is that? Why can we just cover analyze it this way, right? Remember the rules that we state, right? Is the first moment of area cannot cross over the what? The centroid, yes or no? Right? So that's why we don't look at before the centroid, okay? Especially when at this stage, when we are analyzing point A. Okay, so for this reason, we can isolate the top and the bottom because the first moment, or all of this is because of the first moment of area. Okay, now, so the Q on the left hand side and the Q on the right hand side are independent. Okay, so for this case, we know that we're going to find the shear stress at point A It's going to be, we are going to use wide flange analysis.